Welcome to Wings of Arrow Advanced Education and Research Organization. To know more, visit our official webpage www.wingsofarrow.in. Find your dream aviation and aerospace jobs at www.wingsofarrow.in/jobs. Now we are going to learn how to find velocity increments for transfer maneuvers of satellite. Consider a satellite is launched from a circular equatorial parking orbit at an altitude of 160 km into a coplanar circular synchronous orbit by using a Hohmann transfer ellipse. Assume a homogeneous spherical Earth with a radius of 6371 km. Determine the velocity increments for entering the transfer ellipse and for achieving the synchronous orbit at 42,200 km altitude. Given data. So radius of the Earth is 6371 km and a satellite is launched from circular orbit at an altitude of 160 km. Then write orbit radius or suffix a is equal to 6531 km. And satellite is achieved synchronous orbit at 42,200 km above the Earth's surface. Then orbit radius or suffix b is equal to 48,571 km. Now we have to find out the velocity increments for the transfer maneuvers. In orbital mechanics, the Hohmann transfer orbit is an elliptical orbit which is used to transfer between two circular orbits of different radii in the same plane. And a synchronous orbit is an orbit in which an orbiting body has a period equal to the average rotational period of the body being orbited and in the same direction of rotation as the body. To find the velocity increments, we must calculate the major axis of transfer ellipse, orbit velocity and transferring velocity changes. So the major axis of the transfer ellipse can be written as a suffix te is equal to 1 divided by 2 into r suffix a plus r suffix b. Now solve this equation with given values. We get the major axis is 27,551 km. For a circular orbit, the satellite velocity is found by the square root of mu divided by r, where r is the instantaneous radius from the center of the Earth and mu is the Earth's gravitational constant, which is 3.986 into 10 to the power 14 meter cube per second square. From this, the orbit velocities of the two satellites can be calculated. Now substitute the values and solve. We get the orbit velocities for two orbit radius. U suffix a is equal to 7788 meter per second and u suffix b is equal to 2864.7 meter per second. The circular orbit is a special case of the more general elliptical orbit. The Earth or any other heavenly body around which another body is moving is located at one of the focal points of this ellipse. The relevant equations of motion come from Kepler's laws. And elliptical orbits may be described as follows. When expressed in polar coordinates, u suffix te is equal to square root of mu into 2 divided by r minus 1 divided by a, where u is the velocity of the body in the elliptical orbit, r is the instantaneous radius from the center of Earth, and a is the major axis of the ellipse, and mu is the Earth's gravitational constant. From this, we can calculate the velocities needed to enter and exit the transfer ellipse. Substitute the values of two different radius and solve. We get the velocity needed to enter the transfer ellipse. U suffix te suffix a is equal to 10,337 meter per second, and velocity needed to exit the transfer ellipse u suffix t e suffix b is equal to 1394 meter per second. Next, find the velocity changes. So here the changes in velocity going from parking orbit to ellipse delta u suffix a is equal to 2549 meter per second, and velocity changes from ellipse to final orbit delta u suffix b is equal to 1471 meter per second. Now by adding those velocity changes, we can get the velocity increments for transfer maneuver. Then the required velocity increment is 4020 meter per second. Did you know? This was the test launch for ISRO heaviest and upgraded rocket, the GSLV Mark III, which is carrying the Crew Module Atmospheric Re-entry Experiment. The Rs 155 crore mission has twin purposes. The main purpose is to test the rocket's atmospheric flight stability with around 4-ton luggage. The second is to study the re-entry characteristics of the crew module, called Crew Module Atmospheric Re-entry Experiment. GSLV Mark III is the heaviest next-generation rocket, conceived and designed to make ISRO self-reliant in launching heavier communication satellites of INSAT-4 class, which weigh 4,500 to 5,000 kg. Once operational, this rocket will have the capability to ferry 4-ton class of INSAT series of communication satellites, which are currently being launched through Arianespace.
If you have further inquiry or requested video, drop down to our mail wingsofarrow@gmail.com. Don't forget to subscribe for more updates. For the time being, take care, stay blessed, inspired, and fly high.